In this video, we're going to go ahead and talk about one of the main geometric applications of integration, and that's going to be how do we find the area between two curves in the plane? So the idea is that you'll have one, two, or even several curves in the plane. You want to figure out the area between them, and we can actually do that with the help of some integrals. We have a few problems that we'll demonstrate here and how to do that. So let's go ahead and start here. For all of these, I've already gone ahead and drawn the picture of both the curves here using MATLAB. You can do this in your favorite graphing calculator of choice. The first one is a basic warm-up one. So we have already sketched a region bounded by these two curves, y equals 2x, which is the line here in blue, and the parabola y equals x squared minus 4x, and that's here in orange. Y equals x squared minus 4x. And we want to find this shaded magenta area between the two. So we've already sketched the region, but now we need to figure out how to find this area. And so what we should imagine here is that we've sliced this region into a bunch of rectangular strips. For example, we say that we sliced it here as a vertical strip in black, and this strip can sweep right to left. We want to figure out where does this strip range as far as its x values. And to do that, we need to figure out what these intersection points are. And to do that, we know that two curves will intersect if they have the same x and y values together. And notice that we have already these solved for y, so we can go ahead and set these two equal to each other to figure out what the intersection points are. So when we do that, we'll have x squared minus 4x equals 2x. We just set those two equal to each other. And now we're just going to go ahead and manipulate this and solve for x. This is a quadratic. We'll go ahead and subtract 2x from both sides. We have x squared minus 6x equals 0. And now I have a common factor of x on the left-hand side, so I can go ahead and factor that out. So we have x times x minus 6 equals 0. And we remember some of the basics from algebra, right? Whenever I have a bunch of things multiplied together, that multiply to 0, and I know that at least one of those factors is 0. So that means we have x equals 0, or x minus 6 equals 0. And of course, in the latter, we have x equals 6. And if you look in the picture here, that does agree with the ranges here. That agrees with the x intersection points here. And what these are going to help us do is set up our integral, because these are our limits of integration. Remember that black strip moves left to right. But now how do we set up the integral? Well, the main thing to remember here is that when talking about area between curves, we need to remember top minus the bottom. Top minus bottom. That's going to be the main idea here. And as we see here in our picture, the top of this black strip is on the blue curve. That's the line. And the bottom is on the parabola in orange. And so to set up our integral for our area, we're just going to do top minus bottom, in this case, blue minus orange. So the area here will be the integral from 0 to 6, because that's where our region is bounded from in the x direction. The top curve, which is 2x, minus the bottom curve, which is the parabola. We'll go ahead and put all that in parentheses here, because we need to subtract all that away. And now we just go ahead and distribute the minus sign through and collect some like terms. So we'll have 2x minus x squared plus 4x dx. 2 plus 4 is 6, so 2x plus 4x is 6x. So we are now left with this simple looking integral here. 6x minus x squared x. And this is a combination of two simple functions here. And so I'm just going to put this off here to decide to remind us about the power rule. When we integrate something that is of the form x to the n dx, all we need to do is add 1 to the exponent, so x to the n plus 1, and then divide by n plus 1, new exponent. And then, of course, that's plus a constant. So I've expressed this here as an antiderivative, as an indefinite. But of course, since we're doing a definite integral, we're getting a number out of this. So we don't need the plus c. But if we just follow that pattern here, well, let's take a look here what we get. So an antiderivative of 6x, so it'll be 6x squared divided by 2. Go ahead and write that out in full. Of course, you can simplify that to 3x squared. Okay. And then an antiderivative of x squared is going to be x cubed over 3. Go ahead and evaluate this on the boundary between 6 and 0. And then we do the top evaluation, and then we subtract away the evaluation at the bottom. So let's go ahead and write that out in full here. So we have 6 times 6 squared over 2 minus 6 cubed over 3. And then when we plug in 0, well, that is 0 in this case, but we'll go ahead and write it in to see what happens anyway. Okay. Minus 0 cubed. And now I can just punch this into my favorite calculator of choice. Okay, keeping in mind the parentheses here with the grouping symbols. And when we do all that work, let's see what we get. So I will have 6 times 6 squared divided by 2, and then minus 6 cubed divided by 3. Turns out that all we get is just 36. And that is the area between our two curves here. So that magenta area that we were trying to find before has area of 36. And so now let's see what happens with a different kind of problem here. Again, I have two curves here. This time it's two parabolas. Note that we both have x squares there, so we have two parabolas there. The parabola in blue here, okay, you see that the lowest y value is 0, so that one is clearly y equals 4x squared. And then the parabola in orange there is x squared plus 3. Go ahead and put that there. And as usual, I need to first find those two intersection points on the x direction, because these help me determine my magenta area where it's bounded between. And let's go ahead and draw in one of those little representative black rectangular strips here. Again, the strip moves from left to right. And we can see here in the picture, it looks like the region of integration is going to be between -1 and 1. But we should go ahead and verify that, okay? So just as usual, we'll go ahead and set these two equal to each other. The 4x squared equal to x squared plus 3. This is a simpler looking kind of quadratic. There's no linear term here. We just have a quadratic term and a constant term. Let's just go ahead and go through the usual process here. So we'll move everything over to the left. We have 3x squared minus 3 equals 0. I see I have a common factor of 3. So we can just factor that away. And now x squared minus 1 is a very special factoring pattern that we should remember. Our favorite difference of squares, which I'll write up here in the margin. A squared minus b squared is the same as a plus b times a minus b. And so that x squared minus 1 factor can be written as x plus 1 times x minus 1. And once again, we use our zero product property to take those factors, set them equal to 0. So we get x plus 1 equals 0, and x minus 1 equals 0. So we get x equals minus 1, and x equals 1, as expected from the. So this is how you find those points of intersection. You need to actually set the two curves equal to each other. You're really solving a system of two equations. Make sure that you're following the rules for that. And that gives you your intersection point. Now we'll go ahead and set up our integral for our area. Let's get a little bit more space here. So our area here, which I'm calling A, is the integral from -1 to 1. Okay, that's the lowest x value, the largest x value. Okay. Now I need to do top minus bottom. Here, the top curve is in orange. That's where the top of the strip is. And the bottom one is in blue. So top minus bottom here, x squared plus 3 minus 4x squared dx. Go ahead and collect some like terms here. We'll have 3 minus 3x squared dx. And once again, we invoke our power rule, our simplest integration rule that we have. An antiderivative of 3, well, that's just going to be 3x. Then an antiderivative of 3x squared, that's 3x cubed over 3. which I'll just write as 3x cubed. Okay? Again, keep in mind here, right? That's 3x cubed over 3 is the same as x cubed. We just added a 1 to the exponent and divided by the new exponent. I'm going to evaluate this between 1 and minus 1. And so we'll go ahead and set up our evaluations here. Just plug in the corresponding x values and subtract. Now, of course, you might be able to see some symmetry here in the picture, and you can invoke that as well. But you should be very careful to remember that when you're integrating an even function over a symmetric interval, as one like this, you just integrate from the center out to the edge and multiply that by 2. I won't show that here, but it's a very good exercise to write out the problem in full, okay? Now, we just punch this into our favorite calculator. These aren't too bad. So we have 3 minus 1, then minus, well, 3 times negative 1 is negative 3. Negative 1 cubed is a negative 1. Okay, we verify that by punching it into your favorite calculator. Then we have a minus sign in front of that, so that's a plus 1. 3 minus 1 is 2. Negative 3 plus 1 is negative 2. So 2 minus negative 2, which is 4. That's our area. As you can see, you just have to remember the basic mantra, top minus bottom. If you can draw your representative strip like this, you can see where the top of the strip touches, the bottom of the strip touches, and that gives you the distance between. That distance is just going to change as we sweep across. All right. Now, you may have seen some problems where you have multiple regions, these so-called bow tie regions where things will intersect. For example, maybe if I include this extra bit here, well, then you have to set up some extra integrals here to include this. But again, the mantra is the same, top minus bottom. You just separated it out into two regions and glue the pieces back together by addition. So now we can go on to another type of problem, where instead where we have curves that are expressed as functions of x, we might have a curve that is expressed as a function of y, or something that's probably put into a so-called standard form. So we have a parabola and a line here. And so let's go ahead and put in labels here. The line is in orange here. That's the line x minus 2y equals 3. And the parabola is in blue. That's y squared equals x. That is our favorite parabola, just turned sideways. And of course, now we want to think about the area in these two curves. So that's, again, this magenta region here. Now, if we took the same approach as we did before, write everything as a function of x and set things equal to each other, we're going to come into a problem where here, in some part, if our strip here is oriented there, we'll notice that it touches the parabola at both the top and the bottom. See, this is not a function of x here. This is a function of y, okay? In fact, if you tried to solve this thing for x, excuse me, solve it for y, we'll technically get y equals plus minus square root x because you have two branches of the square root. Okay, the plus branch is the top half, the minus branch is the bottom half. And this kind of makes the work a little bit more difficult for us. And so here we're actually going to go ahead and change the order of integration. Okay, just using some language from Calculus 3 there. We're going to go ahead and change the order of integration. So instead of integrating at x, we're going to integrate in y here out of convenience. And so what that means is instead of having a strip that is oriented vertically like we had in the last two, we will now have a strip that is oriented horizontally. So that's this one right here. And now instead of top minus bottom, the mantra now becomes right minus left. So let's go ahead and write that in here. Right minus left. Okay, whenever we integrate with respect to y, we're now thinking right minus left. We should also think here that the strip moves up and down. So we're going to go from a lowest y value, highest y value. We might be able to see what it is in the picture, but let's go ahead and solve it algebraically. So we're going to go ahead and set these two things equal to each other. Okay, or in fact, just use substitution here. Notice that I have something here already solved for x, and so I can just toss it in. So looking at this system here, y squared equals x minus 2y equals 3. And so now by substituting, okay, I get y squared minus 2y equals 3. And now I can just go ahead and move stuff over to the left-hand side. So y squared minus 2y minus 3 equals 0. And we can factor this. Okay? So two things that multiply to negative 3 and add to negative 2. Okay, well, our magic numbers here are negative 3, a positive 1. So we see that we'll have y minus 3 equals 0 and y plus 1 equals 0. Okay, and now we solve both of those two independently. Y equals 3 and y equals minus 1, as seen in the picture. So those are our y values. Those are our limits of integration. And now we can go ahead and set up our integral here. But let's get everything in terms of functions of y now, okay? So we want to get everything as x equals a function of y. Okay, I want x equals some function of y here. Well, I already have that for the parabola here. Okay, but for the line, which is an orange, okay, let's go ahead and manipulate that a little. We have x minus 2y equals 3. And I want to go ahead and write this so that I have x equals a thing. Well, I just want to get x by itself, and the only thing I need to do here is just add 2y to both sides. So I get x equals 2y plus 3. Let's write it like that, 2y plus 3. Okay. Now I have all the pieces that I need, okay? Using the right minus left mantra here, we can go ahead and set up our integral. So the area here, let's switch colors. Let's scroll down a little and punch out a little. Go. Okay, so the area here is an integral. Now we're integrating in y, so instead of moving from left to right, I'm not sure if you can see this on the camera, but instead of moving left to right here like this, now moving up and down. Okay? So with that being said, we're going to go from our lowest y value, which is negative 1, our highest y value, which is 3, and we're thinking right minus left. Let's do this in that same color. So right as a function of y, okay, 2y plus 3, minus left, okay, so minus y squared dy. Go ahead and, well, there's nothing for me to combine even after I drop the parentheses. Okay, so we can just go ahead and use our power rule. So an antiderivative for 2y, well, that's y squared. An antiderivative for 3, that's 3y. And then minus an antiderivative for y squared, y cubed over 3. We do our usual thing here, evaluate on the boundary. And it's always a good idea when you do these problems, right? When you're first starting out, go ahead and write down what you should type into your calculator. Okay, that way there's no mistakes of user error here. So we'll have 3 squared plus 3 times 3 minus 3 cubed over 3. Lots of 3's there. And now minus, this is where we got to be careful, negative 1 squared plus 3 times negative 1, then minus negative 1 cubed over 3. Okay, this isn't too bad to work out by hand. In fact, 3 squared is 9. 3 times 3 is 9. So 9 plus 9 is 18. Minus 3 times 3. Well, that's going to be 3, 9, 27. Divided by 3, that's 9. So 3 cubed over 9 is 3 cubed over 3 is 9. And now minus here, let's be a little more careful. Okay. Negative 1 squared is a positive 1. Plus 3 times negative 1, that's going to be a negative 3. Negative 1 cubed, okay. Negative times a negative is a positive, times another negative is a minus. But then I have the extra minus sign there. That is a net plus 1/3. Okay. And now we can just go ahead and punch this in. Okay. Or you can see that we'll get, let's see, 18 minus 9 is 9. Then minus 1 plus 3 minus a third. Okay, we will have 9 minus 1 is 8, plus 3 is 11. And we're subtracting away a third. we just go ahead and write 11 as 33 over 3. Let's actually show that there. In the end, we get 32, 3 as our area. And so we still get the same thing. In fact, I'll leave it as an exercise that once you see the next two problems, okay, try to do the same process in x. You'll have to chop this off into two integrals, but you should still get the same number here. Okay, the key here is when you do this, okay, make sure that you have a picture that shows you what you're doing. You found the intersection points algebraically, so you get something accurate. Okay, you have everything in the correct form here. In this case, everything is a function of x. I mean, everything is a function of y. And then you set up your integral, and if you have to, write down what you'll be plugging into your calculator. So now let's move on to some interesting here. Okay, this is going to be an exercise of what happens when we change the order of integration out of convenience. So if you can see, what we have now is two curves, again, a parabola and a line. So let's go ahead and label those here. Okay, the line is in blue, and the parabola is in orange. And I've gone ahead and copied the same picture twice, okay, for both parts A and B here. So that way we can use that to visualize our slicing of our region here. So we want to set up an integral here, but this time we're going to first integrate with respect to x. Okay, what that means is we should have an integral of some function dx. But how do we do that? Let's go ahead and first consider our region here. And the magenta. And I want to integrate this in x. Well, as we saw in the last picture, right, there's going to be a point where the strips here do not touch both of the curves, but rather touch the same curve twice, as it does here. And so what we do is we have to cut this up into two different integrals. In fact, let me go ahead and change the color here a little. There's our intersection point. We have our line there. And this dark blue is going to be where we're going to make our cut. And then we'll still have a vertical strip here, but that vertical strip touches the orange curve in both places. But the thing is that the orange curve does not represent a single function of x, it's two branches. So we're going to have to do a little bit of work. Well, let's first go ahead and try to see what these intersection points are, okay, on the curve here. We can also sort of clearly see that the parabola here in orange does hit uh, the y-axis at y equals 0. But we can, of course, excuse me, at x equals 0. But we can go ahead and verify all this. So we'll go ahead and use that same substitution method as before, right? I already have something solved for y. And so I can plug that entire expression in there. So we'll have 4x plus y, which is 2x plus 4 squared, equals 0. And I'm now going to go ahead and just expand using our favorite rule here, which I'll go and write down. A plus b squared, that's just a squared plus 2ab plus b squared. If you need to remind yourself of that, okay, go ahead and write down a plus b times a plus b and distribute properly with the multiplications. If we use that rule here, we'll have the first thing squared, so 2x squared is a 4x squared, plus 2 times the first times the second. 2 times 4 is 8, times 2 is 16, x, then plus the second thing squared, 16. Okay, so let's go ahead and collect some like terms here and shuffle these things so it looks a little easier to read. 4x squared plus 20x plus 16 equals 0. And notice that I have a common factor of 4. I have a GCD here. We'll pull out the GCD, and the inside will have x squared plus 5x plus 4 equals 0. And that looks a little easier to work with. I can factor that. Okay. Two numbers that multiply to positive 4 and add to positive 5 are 4 and 1. And so our intersection points in the x direction, keyword there, are negative 4 Okay, x plus 4 equals 0, so x equals minus 4, and x equals minus 1, as we see in our picture there. Now, of course, we'll still need to figure out the second part there, which I should probably call area B here. Okay, and I'll call this first region area A. And so we're going to have two integrals here. The integral for A, we'll do a magenta. So the integral for A in that region will have top minus bottom. So we're going from -4, -1. The top curve is the line, y equals 2x plus 4. But how do we represent the bottom curve? See, we want to represent the bottom curve as a function of y, excuse me, as a function of x. So we'll go ahead and take this thing. Let's go off to the side here and do some side work here. 4x plus y squared equals 0. I want to go ahead and solve this for x, so I subtract 4x both sides. I take the square root, but when I take the square root, I need to include the plus minus here because it's two branches. Now, you might be saying to yourself, I can't take the square root of a negative number. Well, that's true in the real numbers, but notice here that I have x is negative here and the coefficients here are negative. Negative times negative is positive, so everything's fine. But in fact, we only want the bottom branch, okay? This is only the bottom branch of the square root, so we'll take the minus branch here. And so our bottom curve, so to say, is minus square root minus 4x dx. Let's go ahead and tidy it up a little bit. 2x plus 4 plus square root of minus 4x dx. That's just the first region. We need to consider region B here, which considers both the top branch. I'll go ahead and indicate there. The top branch is a plus square root negative 4x. And the top branch is going to be considered the top boundary of the curve here, where that black strip is. And the bottom branch, the minus branch, is the bottom part of the curve. So here we'll integrate from -1 to 0. Okay, those are our x values. Top curve, so that's square root of minus 4x, minus the square root of minus 4x dx. Well, negative negative is a plus, and I have two copies there. So this is what the second integral is going to be. So let's go ahead and combine these two things here. So total area is two complicated integrals. -4 to -1, 2x plus 4, plus the square root of negative 4x dx, and then plus the integral from -1 to 0 of 2 square root of minus 4x dx. Now, this looks a little hard to do, right? It's two integrals of two different functions over two different intervals. But that's what's needed for this one if we want to slice it this way. But there is an easier way to attack this problem. Okay? Instead of slicing and integrating with respect to x, we'll go ahead and slice so we integrate with respect to y. Let's go ahead and demonstrate that just like we did in the last problem here. So same picture, but now I'm going to go ahead and slice my region that I have strips oriented horizontally. These strips move up and down. And I don't have to worry about cutting this region up into two different pieces because the strip will always be touching the orange curve on its right and the blue curve on its left. So I'm only worried about one integral. The only change that now we have to make is since we're integrating with respect to y, we still need those intersection points. Those are intersection points in y. Okay, so the way we find that, since we already have the x intersections here, okay, again, the x intersections are at -4, at -1. Since we found those in the previous part here, we can actually use that to help us figure out what the corresponding y values are. And since they intersect there, we can use only one of the curves here to help us out. And so I'll go ahead and use the line here since that's less computation. So we remember that we have y equals 2x plus 4. Okay, so when x is equal to -4, we get y equals, well, let's see what we get here. 2 times -4 plus 4. We have -8 plus 4, which is -4. That agrees with our picture there. And when x is equal to -1, same deal. Plug in x equals -1 into the line. -2 plus 4, which is a positive 2. Okay, so now I know that I'm integrating from from -4 to 2. So let's go ahead and set that up there. But now I need to express those curves as functions of y now instead of functions of x. Okay. Well, for one of them, it's actually pretty easy. And in fact, I think it is easy for both of them. Ah, yes, it is. Okay. Got to be a little careful here. So let's start with the line here, which is again in blue. So y equals 2x plus 4. I want to solve this for x. So we'll subtract 4 on both sides. Y minus 4 equals 2x. And then we'll divide both sides by 2. And I'm going to write this intentionally in a certain way. We'll have x equals 1/2 times y minus 4. Okay, this is expressing that same curve, that same object as a function of y now. Okay, if this looks familiar to you, this is like finding the inverse function. Okay, remember that from algebra, finding the inverse function where you swap x and y. Now let's work with the parabola. It might take a little more work, but we got it. We have this thing, 4x plus y squared equals 0. And I'm going to go ahead and solve for x here. So let's subtract 4x on both sides. So we have y squared. Oops. Eraser. Here we go. We have y squared equals minus 4x. Now I can divide both sides by -4. So we'll get x equals, I'll write it like this, -1/4 y squared. And that is our boundary curve for the parabola in orange expressed as a function of y. And now all I need to do is do right. This is kind of nice how I wrote this here. Right minus left. And it's only done in one integral. So we have the area here as the integral from -2 to 4 of the thing on the right, -1/4 y squared, minus the thing on the left, 1/2 y minus 4 dy. So I've expressed the same thing two different ways. Okay, we found the area of this region by slicing it in x, but that requires two integrals, as we saw up here. And I've also expressed it as one single integral in y. And now for the punchline to find the area of this region, well, it doesn't really matter which one you do. An exercise to do both of these, okay, to find the area of this region. I'd rather compute one integral, okay, and that's this one here. So let's go ahead and work with that one. So let's go ahead and copy this over, okay, so we don't have to write it again. Okay, there we go. That's our area. Now we just use our power rule again. In fact, what I'll actually do first here is I'll actually multiply the 1/2 through the second term, just to make it a little easier for us to see. We'll have -1/4 y squared, and then -1/2 y. Okay, now -1/2 times -4, that's a positive 2. And now it's just the power rule again. Okay, so -1/4 y cubed over 3. So we can write that as -1/12 y cubed. And then minus an antiderivative of 1/2 y, that's y squared over 4. We'll write it like this. And the antiderivative of 2 is 2y. Okay, we'll go ahead and evaluate on the boundary. And just to do what I did last time, I'll go ahead and write down what the evaluation step looks like. That way we all know how to punch it into our favorite calculators without any error. Okay. So we will have negative 1 over 12 times 2 cubed minus 1 over 4 times 2 squared plus 2 times 2. And now we plug in the lower limit here. So that's going to be minus 1 over 12 times negative 4 cubed. Note the parentheses there. Okay. Minus 1 over 4 times minus 4 squared. Let's fix that a little bit. Okay. Erasers back to normal. Square. Then plus 2 times negative 4. Okay, we can do all this in stages, which I encourage us to all do. Okay, but if we do all the work, okay, and I will leave that part there for you all to verify that this is indeed what it comes out to be. So we'll have minus 1 over 4. Go ahead and use your favorite computing device here. Okay, when we do all the work here, when we simplify all this mess, we get 9 as our area. So even though it may have looked a little scary, just doing one integral does the job easily, and we don't have to worry about evaluating on one interval, whereas in the integral in x, we would have to do it in two. Okay, but as an exercise, go ahead and do this integral. You may need some u substitutions here, but go ahead and do this one here and verify that you do indeed get 9 as the area. So we have one more here. It's a very thin region. I tried my best to graph this here, but it's this let's actually punch in a little bit here. It's this very, very small region here between the line and the parabola here. So let's go ahead and do the same thing here. We'll just go ahead and color in our thin sliver of plane here. And again, I want to find the area of this region, but we're going to set it up as an integral in two different ways. And then we'll pick the order of integration that is more convenient for us. So I have a parabola in blue, a line in orange. So now the colors are swapped here from what they normally were. I want to integrate this thing with respect to x. Well, we should probably go ahead and first figure out what the intersection points are. And I'll actually go ahead and knock out both the x and y intersection points here so that we're all ready to go for the next problem. Okay, again, we can do this by reading it off the graph, but we should verify this algebraically. Okay, so lots of ways that you can do this here. I'm going to find it easier to solve the first equation for x, okay, which we'll need in a second anyway. So we'll have x equals 2 times y minus 2 square minus 1. And I'm going to substitute that into this other equation here. So this gets substituted there. And when I do that, I'll have 2 times y minus 2 square minus 1 plus 6y equals 7. And let's go ahead and solve this equation for y here. And I'll go ahead and do a bit of a quick cleanup here. So 2 times y minus 2 square. I'm going to add 1 to both sides. Okay, so then plus 6y equals 8. 7 plus 1 is 8. And notice here that I do have a common factor of 2, which I'll just go ahead and take care of. I'll just divide through by 2 here. 3y equals 4. And now the squaring process is a little easier here. So y squared, well, here we're just again going to use that perfect square pattern. Y squared minus 4y plus 4 plus 3y equals 4. I see that I have 4 common on both sides. So if I subtract 4 on both sides, those vanish. And I'll collect the like terms there. Y squared minus, let's see here, y squared minus y equals 0. We have y times y minus 1 equals 0. Y equals 0, y equals 1. And that, of course, agrees with our picture. We'll need that for the integral in y. But I want the x coordinates here since I'm going to be integrating with respect to x. And so I'll go ahead and plug these y values into one of the things, probably the line, because that's a little easier. So when y is equal to 0, okay, we'll get that x equals 7. And when y is equal to 1, well, we'll have x plus 6 equals 7. That means that x equals 1. So we are integrating between x equals 1 and x equals 7. Okay. Now, we still have an extra bit of a problem here. The line here is easy to solve for x because we want this to be functions of x. Excuse me, solve for y so we can get a function of x. And when we do that here, I'll subtract I will subtract x on both sides and divide by 6. So we'll end up getting y equals 1 over 6 times 7 minus x. Okay, that's fine. But now I need to solve this second one for x here. And that's a little bit of trickier. So if we do that, okay, I'm going to go ahead and solve this one for x here. Sorry, solve it for y. So we'll first divide through by 2. So x plus 1 over 2 equals y minus 2 square. And then I need to take the square roots. Well, again, when I take square roots, and I introduce a square root, I have to consider both plus and minus. So the question is, which branch? Now, if you fully graphed out this curve as it was given in standard form, this is again a parabola that's sideways. And it turns out that this blue part here is the bottom half. So we're going to take the negative branch of the square root, okay, since it's the bottom half of the graph. So when I take the square root here, I'll have negative square root of x plus 1 over 2 equals y minus 2. And now I just add the 2 over, so I get y equals 2 minus the square root of x minus 1, x plus 1. And so that was a lot of work. But we had to do it to make sure that we got the correct branch of the square root. And now we think about our top minus bottom thing here. And here's our strip. Top is orange, bottom is blue. So the area here, represented as one single integral here, 1 to 7. Again, we're integrating with respect to x. Okay. So we're going to do top minus bottom, so orange minus blue. That's line minus parabola. So 1 over 6 times 7 minus x. And then minus 2 minus the square root of x plus 1 over 2 dx. So it's one integral, but it looks a little messy. Let's see if the integral in y is a little easier to do. So we'll go ahead and take all the work that we did here. So in this case, for the integral in y, I'm going to have those y values of integration here. Those are the intersection points. And again, remember that a strip is oriented horizontally from left to right. And now I want to express everything as a function of y because we're integrating in y. Now, for the line, it's actually easy to do. Okay, I need a function of y there. So what I need to do here, let's write down the original line here. So x plus 6y equals 7. Okay, I want to get x equals some function of y. That's actually easy to do. I just subtract 6y over, and I get x equals 7 minus 6y. That's my line. But for the parabola, it's a little bit of work. Let's copy down what we have there. X plus 1 equals 2 times y minus 2 squared. Well, this one's actually not too bad. To get x equals a function of y, just subtract 1 over. X equals 2 times y minus 2 squared minus 1. And now we can look at what our area is going to be. Lowest y to highest y, again, it's from y equals 0 to y equals 1. And then the curve on the right here, well, the orange is on the right. The right minus the curve on the left, which is the parabola, dy. One integral again, but this one actually looks a little friendlier. This one does look friendlier to handle. And in fact, to find the area of this region, I will actually go ahead and use the integral in y here, because it's easier out of convenience. As an exercise, I encourage you to do the integral in x. So let's go ahead and find that integral. So we go ahead and start here. And I did not copy the 1 over, and that's fine. So now let's go ahead and collect some like terms here. So 7 minus 6y, okay. Now I'll have minus, let's be a little careful here. I'll distribute the minus at the end later. So y square minus 4y plus 4. So we do the square first. Minus 1. Now we just keep going. I'll multiply by 2 first. 2y squared minus 8y plus 8. We still have the minus 1 left over there. Now let's go ahead and do some cleaning up here. We can see here we have 8 minus 1 is 7, and then 7 minus 7 is 0, so that's gone. I'll have minus 2y squared. Then it looks like we'll have a plus 8y minus 6y, a plus 2y, and we're basically home free here. Okay, an antiderivative of minus 2y squared is minus 2y cubed over 3. Then an antiderivative of 2y is y squared. Evaluate that between 1 and 0. You can eyeball it here and see that the evaluation at 0 is indeed 0. Okay, and the evaluation at 1, well, we have minus 2/3 plus 1, which is indeed 1/3, and that's our area. Okay, the hidden step here, again, if you want to write it down, negative 2 times 1 cubed over 3 plus 1 cubed, sorry, 1 squared, minus 2 times 0 cubed over 3 plus 0 squared, and then it evaluates nicely. And so the punchline is the area of this region between the two curves is 1/3. We found it by using the simpler looking integral here in y. So the moral of the story is, depending on how your region looks, you may want to change the order of integration. Okay, we learned that in Calculus 3. You'll want to change the order of integration to integrate in the other variable to give yourself a simpler looking problem. You got to do a little bit of work in inverting the function, but it's at the cost of going from an integral that may look nasty, something that looks a little cleaner, or even better, reducing two integrals over two different intervals into one integral over one integral. And so hopefully we're a little more comfortable now with how to find the area between two curves. And these principles will carry over when we start talking about volume. Okay. What's the main idea here? Top minus bottom, right minus left. See you all in the next one.